Or is the universe something more? A place where the laws of physics include a non-computable element of spontaneous state selection, a process that the brain has uniquely evolved to harness? For decades, this has been a fascinating but largely philosophical debate. For decades, the chasm between computational and quantum theories of consciousness seemed totally unbridgeable, a domain of pure philosophical debate. Proponents of models like GNW and IIT argued that consciousness is all about the pattern of information, while OR proponents claimed it was about a physical process tied to gravity. But without a way to actually test these competing claims, the conversation stayed kind of stuck. I mean, how could you possibly design an experiment to distinguish between a complex algorithm and a gravity-induced quantum collapse happening deep inside a neuron? The beauty of the OR theory, though, is that its radical nature contains the seeds of its own potential falsification. It makes a very specific, very physical, and therefore very testable prediction. The key lies in the central equation of objective reduction tau equals h bar divided by EG. This equation says that the time it takes for a conscious moment to occur, tau, is directly dependent on the gravitational self-energy, EG, of the superposition. This energy, in turn, depends on the amount of mass involved and how far it's separated from itself in the superposition. So, this gives us a crucial variable that, in principle, we can manipulate mass. If we could find a way to subtly change the mass of the components involved in the supposed quantum state without changing anything else about the system's chemistry or computational structure, we could see if it affects the timing of conscious processes. And this is the experimental showdown we've all been waiting for. This leads to the design of what we can call the mass invariance test. The logic here is beautifully simple. First, you identify a neural correlate of consciousness, a measurable brain activity that's tightly linked to conscious experience. A prime candidate is the 40 Hz gamma band brainwave, which OR specifically associates with the frequency of its collapse events. A 25 millisecond collapse time corresponds to a 40 Hz frequency. Then, you run the experiment under two conditions. In the control condition, the brain operates normally. In the test condition, you increase the mass of the specific molecules that OR claims are creating the superposition, namely the tubulins within the microtubules. The crucial constraint is that this mass change must be the only significant change. The chemistry, the electrical properties, and the overall structure of the neurons have to remain identical. If consciousness is purely computational, as GNW and IIT suggest, then this subtle change in nuclear mass should have no effect. The brain's algorithm doesn't care about the weight of the atoms carrying the bits, only about the logic of their interactions. But if OR is correct and consciousness is tied to gravitational collapse, then increasing the mass should increase the gravitational self-energy, EG, which in turn should shorten the collapse time, tau, leading to a measurable change in the frequency of conscious moments. So how can we possibly increase the mass of tubulin proteins inside a living neuron without altering their chemical function? The answer lies in a clever biological trick using isotopes. Isotopes are versions of an element that have the same number of protons but a different number of neutrons. This means they have a different atomic mass but nearly identical chemical properties. For example, the most common form of carbon is carbon-12 with 6 protons and 6 neutrons. But there is also a stable, heavier isotope, carbon-13, which has an extra neutron. A molecule built with carbon-13 will be slightly heavier than its normal counterpart, but it will form the same chemical bonds and participate in the same biochemical reactions. The experimental strategy, then, is to enrich the building blocks of tubulin proteins with heavier isotopes. We could raise organisms or prepare brain slices in an environment where the essential amino acids used to build proteins are synthesized with carbon-13 or nitrogen-15 instead of their lighter, more common isotopes. This process, known as isotopic labeling, would result in microtubules that are physically heavier but chemically and structurally unchanged. This is, honestly, the perfect tool for our mass invariance test. It allows us to tweak the very parameter, mass, that Penrose's theory depends on, while leaving the computational architecture of the neuron, which the other theories depend on, almost completely untouched. Of course, we must be incredibly careful. The experiment needs to be designed to isolate the effect of mass alone. It wouldn't be enough to simply make the entire brain heavier, as this could have all sorts of secondary metabolic effects. The OR theory is specific. It's the mass of the part that is moving in the superposition that matters. The theory posits that certain parts of the tubulin protein shift by a tiny distance. The ideal experiment would therefore only enrich those specific mobile regions of the protein with heavier isotopes, leaving the stationary parts with their normal isotopic composition. This is a formidable biochemical challenge, but it represents the cleanest possible version of the test. With this setup, we have two brains, or two brain slices, ready for comparison. One is the control, built from standard light isotopes. The other is the test subject, with its microtubules weighed down by heavy isotopes in key locations. Both are functionally and chemically identical. Both are presented with the same stimuli designed to elicit a conscious response. We then hook them up to an electroencephalogram or a more direct neural probe and measure the resulting brain activity. The stage is set for a direct confrontation between the two rival paradigms of consciousness. The data from our instruments will now serve as the judge. Let's walk through the prediction made by the OR theory. It is direct, quantitative, and unambiguous. In the control brain, with its normal mass microtubules, the quantum superpositions of tubulin proteins will evolve, accumulating gravitational self-energy, e.g., until they reach the collapse threshold at time tau. The theory posits this tau is about 25 milliseconds, giving rise to the familiar 40 Hz gamma rhythm associated with consciousness. This is our baseline. Now, we turn to the brain with the isotopically enriched microtubules. These tubulins are heavier. When they enter superposition, the amount of mass being separated from itself is greater than in the control case. This increased mass directly leads to a larger gravitational self-energy, ERG.